I hope. Hello? Okay. Damn, this kind of is terrible quality. So, yeah, I guess the quality of the stream might be bad, but I will just continue. So, I'm gonna do a couple things. I have a few to-dos, and a few of them should be easy, and a few of them should be hard. Okay, so let's start with the easy one. So this one, we have to check the case where it kisses the edge and not just the corner. So for this one, I'm gonna do, so what's at this point? Intersects, endpoint side, okay, does intersect. So here I'm gonna do another, let's do kisses edge, because we just checked. And this is where um, there's one edge and either, which ones are equal? These vectors are equal of intersection, wait, intersections at 0 and start or end, I see. So, I'm gonna do that or this. Let's format this guy. Let's see. Yeah, sure. And then let's just make another thing just to make this look nice. Let's call this const kisses. And this is going to be equal to kisses edge. Keep on calling eng and or kisses vertex. So here I'm going to just call this kisses. Alright. So this code right here, where am I? So does segment intersect polygon? It takes a polygon by the points and the start and end point of that polygon, and it'll check all the edges to see if it intersects with them. If there is no edge, then there is no intersection, but there could be a situation where the line segment is perfectly inside the triangle without it intersecting, or whatever shape it is. So you check if there's a point inside. But that's just one case where it's like, oh, that's definitely intersecting. But there's other cases where there are intersections, but based on the logic of how you want the system to work, we don't want line segments that intersect at the point at just a single place to not count as to count as intersections. We don't want them to count as intersections if it just touches the edge. And that's just what we're calling kissing. But that should do that part. So now should be another to do. This one's a bit, I'd probably do this one actually, because this top part, so here's this other to do, which I think is like a hard one, that I'm not too sure if it's easy. I mean, yeah, so like there can be many different types of intersections within this path which needs to be resolved. This can be done by making the graph, inserting intersection points, and following the exterior. Um, Basically, we have this polygon. We want it to be a polygon, but we don't want this polygon to have like edges that intersect. So to solve that, we want to just run around the exterior of the shape. But to do that, it takes a bit of computation and like structuring it. So I'll do that later. Um, let's just do this. So this intersection, so find intersection. It's basically like, I mean, I took some of this from online, so I don't really know what's happening per se. At least with like this part, because this is just some, some geometry that I didn't really want to do. But here we get the determinant, and I think that determines like so the determinant can determine if something's parallel, but in this case, there can be an intersection between two lines that happens between parallel lines, right? And this function we want to return, we want to find the intersection, so like we want to return the point. So if they're parallel lines and they intersect, in your mind you're thinking there's actually going to be multiple intersection points technically, like an infinite number, or I guess a finite large amount of number of intersection points along the path that is overlapping. But there's a specific case where two parallel lines can intersect at just one point. And to check that, I'm gonna do something like if if P1, are these points? Yeah, these are points. If equal vectors, oh god, this might be a lot of code. P1 and P2, so there might be 4 lines of this. So if those are equal, um, what are we gonna do if those are equal? Well, we're gonna say that, um, let's do, um, equal, I hate doing let, um, equal point and let's just let's call this other point one, other point output, other point two, and we're gonna use this. So equal point is equal to P1, so those are equal, and other point 1 is equal to, so P1 and P2, so that should be Q1 and output point, man, let's delete this, other point, I feel like output, fudge, it's just really hard, type out, and let's get rid of that, and this needs to be in here, just conceptually. So it shouldn't matter if it happens multiple times, because in theory, okay, yeah, the check shouldn't matter if it. Oops. Yeah, I have an ergodox, and I'm just kind of learning it, but I feel like the control being on the Z is kind of weird. So I did P1, P2, P1, Q2, P1, P2, P1, Q2, Q1, Q1, P2, Q2. And then I have to. And then I have to get this right. Equal point is P1. Other point is P2. Right. Equal other is that one, and then P2 is that one. So equal point is Q1, other point is P1, and other 2. Okay, cool. Q1 equal point is Q1, other point is P1, and this one should be P2. Damn, I guess using P's and Q's are kind of like confusing in this situation. Right, P1, P1, Q1, Q1, P2, Q2, P2, okay. And then at the end of this, so if they're going the same direction, I guess the only weird one would be if it's going straight up and straight down. But if so, if equal point, okay, let's just compute some stuff first. So const, I need the direction dx dy, dx equals uh delta 1 equals, let's do const normalized 1 equals vector subtraction, and I think it gets projected onto V1. Okay. I hope this is right. I'll just come back if it's wrong. Equal point and Q1. No, that's so wrong. Other point, point 1. Steal this. Normalize 2. Um, or given two line segments that are parallel, can I show that line segments that are parallel? How do I show that? How do I show that they point opposite directions? The line segment itself is defined by a list of by two length list of numbers. Let's do JavaScript. What math are you gonna use? So we're gonna dot product. The dot product, okay. But I thought I did the dot product. Determinant A1. Oh, that's different. Take the dot product of it, and then what? So I do the. Wait a minute. I don't even know what that does, but I know what this does. So I do vector subtraction from this base point. I'm just gonna do it my way because I don't understand that. Wait. How do I get the sign value of a number in JavaScript? Sign. So if sign math.sign of normalized 1 at 0 is equal. Damn, I'm coming from Python. Is equal to this guy. Two, and this is also true. I need to check both just in case. I don't know why I feel like I need to check both, but I feel like I have to format that. And I don't want you to return. This shouldn't be should this be tabbed out? That shouldn't be tabbed out, right? Was there an if? I think it's tabbing it because it thinks it's part of the statement. Here I want to return equal point. Otherwise I'd return null because there's a lot of. So if normalized, and then I can simplify this, but the issue is it would be like way harder to understand what's happening. Cool. Point, return equal point. Cool. So now what's hard? So we have this guy. There can be many different types of intersections within this path which needs to be resolved. I don't really want to do that one yet. It sounds kind of hard. I want to get rid of this guy. Build the visibility triangles. So this one might be more fun. Cause am I already sorting it? Sort the edges. So they're already sorted. So basically what I'm gonna do is I'm gonna go through. They're sorted by angle. So I can go vertice to vertice, and So da, 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 da. So what's happening here? Um, what's happening here is I have this visibility graph and I want to get the area that a vertex is visible from. So like I have the vertexes of the terrain in my game, and each one of those vertices of the terrain needs to have some information that the game will use for pathing. And part of that in this like optimized version requires a visibility triangle or visibility triangles for each vertex. And I feel like at some level checking visibility triangles would be a more efficient way of um, detecting whether or not you can see a point. But I think point visibility is probably really easily optimized with quad trees, because at the boundary where you aren't sure whether or not you can path, it's okay to fudge it to make it so that it's a little bit more. It's it's a little bit of a thing, but I just need to get these visibility triangles. And so far, I have a single like. See if I can draw it. So what you have to imagine is you have like. So you have some point, and you imagine that somewhere else in like the world up here, like this area here, there is some other points, some other vertices. So let's go like that. Let's go like that, that. So what you can think of is this is like a visibility triangle, and I want to see what is the shape of this triangle. And yeah, it has to be a triangle, and uh, I mean, I was thinking one strategy would be to take an angle in between that, project a line, get the slope, and then interpolate that against these 2 points to build a triangle. That's one approach, but I also want to leverage the fact that these edges are each one of these vertices that are these like each part of the edge of the visibility triangle, like the vertices of that visibility triangle will be on points on the terrain. So at some level you can do a check to see if 2 points are adjacent. So based on the way that I have this list, so I have a list of edges for each one of these points. And in that list, I sorted them based on the angle around the polygon. So like you can imagine, let's just say that the shape of the polygon was like flat like this. There wouldn't be anything behind this one and this one. Like, so under this area is shape. So there can't even be visibility. So I just need to get the visibility of this area, and at some level I just sorted it based on this one and around to get it so that like around. So with that, I'll let's see, what am I gonna do? How will I solve this? Um, I guess I should just start. So let's iterate over um the path edges, because I need to make visibility triangles. Let's add this. Let's call it cones, because that's actually what it really is, the visibility cones. I hope that wasn't what was making that confusing, that I was talking about visibility cones and not. Yeah. But we get the path edge specific to the thing, and with the same index, we can also get the point, but we don't really need that yet. So with each path edge, so we're gonna also for we're gonna do another for loop, and let's call this edge index and offset, and I'm gonna do element dot length, but I'm gonna call this um edge data. I hate using the word data in a name, but I work I work in this like Python platform for my job, and a lot of stuff is just generic data, so sometimes I will just label stuff data, and it kind of turns into a habit where like things that really shouldn't be labeled data, I'm labeling data because it's just the perfect word. So I actually want to do one less, maybe two less, no, one less, because these triangles, I'm gonna do the diagram again. These triangles, for example, let's do this. How did I do it? It was like underscore, oops. We're doing underscore, then this symbol, then that. Let's just forget the thing for now, because we don't really need it. But so that's 0, 1, 2, 3. We do 0 and 1, 1 and 2, 2 and 3. So we stop before the last. And then we get left. Let's call this const left edge equals edge data at edge index. And const right edge equals edge data edge index plus 1. And with these, I need to get I need to get the line between I mean, I could also I'm gonna take a quick wee. I'm back, and I'm gonna let my cat in. 0. Yeah, clean your shit faster so you can come in here. You don't want to come in? Okay. Yeah, lick your butt out there. Alright, let's come back to my desk. Whoosh. Now... Dang, I'm still solving this problem. So let's solve for a simple case where... So first, let's solve the simple case where the left edge and the right edge are connected with a terrain edge. So these are all indexes, so I'm basically just gonna start dancing these indexes. So like, uh, so const left vertex equals edge equals left edge at 0, but I want to get the vertex. Left vertex. Nah, I'll just keep it indexes. I'm gonna dance on indexes. I did call it right edge. And now I need... So I need to get... okay. So I need to get left edge data and right edge data, which is going to be left edge at 0, path edges, because that's an index. I hate when it goes over like that. Maybe I'll have it set like that. So I get those path edges, and I want... So that's the data. I need to get the first one and the last one. Those indexes for both. So here, const left neighbor. Or I guess I only need to get one to see. So I'll just get the left edge data. So we get left neighbors equals, let's do left edge data at 0. Because that's now okay. And then it's also a dumb way to get the last one. But let's just get the index. So that gets the left neighbors index. If left neighbor index at 0 is equal to Let's do, so it's connected by terrain. If it's not connected by terrain, then the alternative is, oh yeah. Damn, yeah, so it's connected by terrain equals left neighbor. Wait, what's the how to see if a list has an element JavaScript includes left neighbor dot index dot includes. Is this by reference or by value? By value. Cool. If it includes left edge. Wait, what? Okay. So I get the edge data and I have a specific edge. That specific edge, I get the index by going to 0. So I really only need the indexes. So let's just skip that. I wanted to dance on indexes anyways. Left edge index. And then right edge index. Index. That's an index. Includes this index. If connected by terrain. What am I doing here? So I'm building triangles. So a specific edge might have multiple triangles. So I'm gonna do const. It's called visibility triangles, visibility cones. And so I'm gonna do center, left, and right. Edge data visibility cone. So vertices list. Is that what it is? No, path vertices. What are you doing? So I need to get the one at index, dot point, and then the left one, which is left edge index. Let's copy this because that's just going to be right. Right. Alright, so cone is index left edge. Right? I have to use like break and continue. It's the worst. Is it continue that I want to do? I think it is continue. Or do I actually want to split this out into... Nah, I need all this data. Fuck it. So at this point, the back wall of the triangle is either a terrain wall but not at the vertices, so like at the middle, or it extends forever. And either one of these I have to do a line check. Yeah, because there can be a case, let's see if I can do the ASCII for this. But there can be a case where it's like, say you have some wall here, and you have something that's like, oops, it's like, it's like, but, and then down here it's like, but, but, and you'll get a visibility line here, and say you have the same thing here. Oops, I accidentally tapped 1, 2, 3, 4. 1, 2, 3, 4. So you'll get a point here, and there'll be a line. Because there's no vertex in the vision of here, we need to get this right here. But we also know that this has to be the full line, and there can't be another line, because if there was another line, this line would end. Or another line would go in front of it, and you would get a point. So it has to be this line, and at some level, like, we kind of have to first project the line out, see if it intersects. If there is no intersection, then so what I can do is I'm going to, so, uh, what's gonna happen is that we will interpolate. Can't be in front of them, it has to be behind. So we'll interpolate 2 points between the left and right edge. The first point will be casted, and if there is not an intersection, we know it extends forever. If there is an intersection, the second point will determine the line fully, and which can be intersected with the other points with the left, right edge to get the full triangle. Let's make it write some functions for us. JavaScript. Oh yeah, if you can see in my mini map, you might not be able to read it because my rendering is so bad, but there's like these things. You see that? Like it says collider. I think it's kind of fun with the mini map. You can see like, oh, I'm gonna go here or more up. But yeah, I'm gonna continue. Interpolate. Can you write that with the functions in the library? Awesome. You're so cool. Steal you. Oh, I don't want to see there. Huh? Weird. Huh? Wow, it's weird. Scary. Cool. Where was I? Oh, I was doing the full thing over here. At this point, so I need to get. So here's const test point 1. What is the shortening for interpolate? Interp. Get that shit out of here. Boink. Ugh. Left vertex. Right vertex. 0.25. Test point one, test point, test projection, collides, equals, segment, intersection, collider. Uh, I also have the scale. What's the function? Scale point from base point, and it returns the. Okay. Center. How far do I have to scale this? 'Cause maybe it's small, you know? Maybe it's like a small. Const test distance equals distance between test point and center vertex. Whoa, shit just moved. What are you mad about? Const. Scaled test point. Test distance. And this is it's at least 1,000. Fuck it. Let's make it huge. Segment intersects collider. Start end and colliders. Scaled test 0. Scaled test point 1. And what do we have? Segment colliders. Joink. So now, if test projection collides, if it doesn't collide, then to do make up a big triangle and then break. Right? I'm breaking. Oh, it's continue. It's always hard to remember which one I'm doing. And then this is if there is line segment colliders. Is that every? Wait. No. Damn. Yeah, I think this will just be it. This on its own was kind of a lot, but I don't really like factoring out. I mean, this one was kind of chill because I'm using it multiple times, but like test point stuff, I really don't want to refactor because I prefer to like have the whole thing of code in front of me and not click through. I guess for the made up big triangle, I'll just do the same thing I did here. Okay, here, let me, instead of a scale, let's do this with this guy. Can you modify this function to a new function called set distance to, which sets the point to move distance away. No. Oh. Direction. Wait. Okay, wait. It should have this. So set distance, base point, distance, direction, normalized direction, scale vector. Yeah, yada, yada, yada. Scale point from, and then I have a set distance to. Set distance to. I'm just gonna believe that that works. I'll just fix it if it's not working. So here, let me do scale text point equals set distance 2, and I don't need that. Drop U. So I'll just call this const scaled. I'm gonna have to make that something. That 1000. Let's call this stuff the right stuff. Cone, push cone. Send left, right, okay. Continue. So this is expensive, check, medium. Did I uppercase that shit? Medium, check. There. Let's keep this tight. Okay. And this is the simple case. Let's move this shit. Let's move this comment down so I can read it. Finish the visibility graph. Format all my comments. Sweet. For 2 test points, get the nearest intersection with edge. There has to be one at least. I guess I have to return a new function inside of that top part that tells you how many. So that forms the back wall of the triangle, and intersect these with the projected lines. So I think I think that'd be it. And now we're streaming. It's kind of chill.